have you ever stopped and wondered, how we get things so precise in the world? Like, how do engineers know exactly how much fuel a rocket needs? Or how does a factory calculate precisely what they need to make, say, a specific amount of product? It kind of feels like magic sometimes, right? But deep down, it's really chemistry. It's the logic of chemistry that makes it work. So today, we're doing a deep dive into the principles, the really foundational stuff that lets us quantify chemical reactions, how we connect tiny atoms to the amounts we can actually measure.
That's exactly right. And this deep dive, it's really our take on a key chapter from a major chemistry textbook, the one covering chemical reactions and stoichiometry.
Hmm.
Our goal here is to, cut through the jargon, get to the heart of it. We want to pull out the crucial ideas and show how they connect to, well, surprisingly everyday things and some really important applications. The idea is you walk away understanding why this stuff is so powerful, not just what the definitions are.
Okay, let's unpack that then. We should probably start with this word, stoichiometry. Sounds a bit complicated.
It does, doesn't it?
Right.
But the idea itself is pretty elegant.
Its roots are Greek, meaning element measure.
Yeah.
And that's basically what it is, right? Studying the quantitative side of reactions, how much reactant gives how much product.
Precisely. Think about it. It's everywhere. From getting the chemistry right in your morning coffee for the best flavor.
Huh, okay. Maybe not consciously doing stoichiometry there.
Well, no. But the principles apply.
Yeah.
All the way up to launching satellites, where you absolutely need that precision. It's not just about how much, it's about getting it exactly right. That's what avoids waste, prevents problems, and makes industries work.
So what's the bedrock principle behind all this measuring?
That would be the law of conservation of mass. It's fundamental. Basically, it says atoms aren't created or destroyed in a normal chemical reaction. They just rearrange.
Like Lego bricks. You take apart a car, build a house, but you still have all the same bricks you started with.
Exactly like that. Same collection of atoms before and after. It's why chemistry works, why it's predictable. It's like atomic accounting. Without this law, none of the quantitative stuff we're talking about would make any sense. It underpins everything.
Okay, so if atoms are just rearranging, how do chemists actually, write this down? How do they track it all?
That's where chemical equations come in. They're the standard language for this.
Right, you've got the stuff you start with on the left,
The reactants.
reactants, and the
Yeah.
stuff you end up with on the right.
The products.
And there's an arrow in between showing the transformation. Plus, signs mean things are reacting together.
And crucially, you have those numbers in front of the chemical formulas, the coefficients. They tell you the relative number of molecules or moles involved. That's how we make sure the atomic accounting balances out.
And this is where people can get tripped up, right? The difference between those coefficients and the little numbers within the formulas.
Yes, absolute crucial distinction. The subscripts, like the 2H0 for water, they define what the substance is. You change that 2ET to make, say, H0, and suddenly you've got hydrogen peroxide. Totally different.
Dangerous, even.
Can be, yeah. But the coefficients, like if you put a 2 in front to get 2H0, that just means you have two water molecules. It's about the amount, not the identity.
So when you're balancing an equation, you're only ever changing the coefficients.
Never, ever touch the subscripts. That's like changing the ingredients halfway through baking a cake. You adjust the amounts, the coefficients, to make sure mass is conserved.
Got it. So balancing is the practical application of that conservation law, making sure every atom is accounted for. Let's take an example, like methane burning, CH.
Odd one. Methane, CH0, burns in oxygen, ORO, to make carbon dioxide, KO, and water, H2O. The unbalanced equation is just CHO plus ORO plus HRO.
But that doesn't add up, atom-wise.
Right. You've got, 4 hydrogens on the left, only 2 on the right, 2 oxygens left, 3 right. It's unbalanced.
So you adjust the coefficients. A good strategy is often to start with elements that only appear in one reactant and one product. Carbon here.
Exactly. 1 carbon left, 1 right. That's okay. Then hydrogen 4 left, 2 right. So we need to double the water on the right, put a 2 coefficient in front of HO.
Okay, so CH plus O euro plus 2H arrow. Now hydrogens match, but what about oxygen?
Now we check oxygen again. Still 2 on the left. But on the right, we have 2 in co-euro plus 2 in the 2H air. That's 4 oxygens total on the right.
So we need 4 on the left too. We need to put a 2 coefficient in front of the O.
Perfect. So the balanced equation is CH plus 2O plus 2HO plus 2HO. Now everything matches. 1 carbon, 4 hydrogens, 4 oxygens on both sides.
And sometimes you see those little letters in parentheses, right? G, L, S.
Yeah, those just tell you the physical state: gas, G, liquid, L, solid, S, or AQ for aqueous, meaning dissolved in water. Sometimes a delta symbol over the arrow means heat is needed.
It all comes back to making sure that equation accurately represents the conserved matter.
So zooming out a bit, there are countless chemical reactions, but many fall into predictable patterns. Recognizing these helps us predict what might happen.
Like different types of dance moves in chemistry.
Huh. Sort of. Yeah, learning the basic choreography. Let's look at three main types.
Okay, first up, combination reactions. Sounds straightforward.
It is A plus B E C. Two or more things combine to make one new, more complex thing.
Like magnesium burning in air, that bright white light.
Exactly. Magnesium metal, Mg, reacts with oxygen gas, O euro, to form magnesium oxide, MgO. That's 2MgS plus Og, Um2MgS. It's used in flares, fireworks. And typically, when a metal combines with a nonmetal like oxygen, you get an ionic solid like MgO. That's a useful pattern.
What are some other big ones?
Well, carbon burning to make QEO is one. And a really huge one, industrially, is nitrogen and hydrogen combining to make ammonia, NHS.
The Haber-Bosch process.
That's the one. Feeds billions through fertilizers. A massive triumph of understanding combination reactions.
Okay, so if combination is putting things together, what's taking them apart?
That would be decomposition reactions, the reverse. C, A plus B. One substance breaks down into two or more simpler ones.
Like heating limestone, calcium carbonate.
Perfect example.
Yeah.
Calcium carbonate, CaCO, when heated strongly, decomposes into calcium oxide, CaO, that's quicklime and carbon dioxide, CaCO plus co-ures. And quicklime is vital for making glass, cement, steel. Huge industries rely on this decomposition.
Is there a more dramatic example?
Oh, absolutely. Sodium azide. Nana. It's a solid, but give it a sharp impact.
Like in a car crash.
Exactly.
Yeah.
It decomposes incredibly rapidly into sodium, metal, and nitrogen gas. 2 nanos plus 3 andros. That sudden burst of nitrogen gas is what inflates airbags. Just about 100 grams makes 50 liters of gas almost instantly.
Yeah.
Life-saving decomposition.
Yeah, okay, third type.
Combustion reactions. Think fire. Rapid reactions, usually with oxygen from the air producing a flame.
Like burning propane in a BBQ grill.
Classic example. Propane is a hydrocarbon, just carbon and hydrogen, CH. When it burns completely, it reacts with OO to form co-EuroSH, plus 5 O euro, 3 SAGE, plus 4 Ag. Huge amounts of energy released, which is why we use it as fuel.
What about things with oxygen already in them, like wood or sugar?
Good question. Compounds with C, H, and O like alcohols. Sugars, they also typically combust to form kidose and HRO. Our own bodies use glucose, COO. It gets converted to CO and HRO to release energy.
But we're not actually burning inside, right?
Right. It's not combustion like a fire. It's a much slower, controlled series of oxidation reactions at body temperature. Same overall products, very different process.
Okay, so we've got balanced equations, we know some reaction types, but these are all about individual molecules. How do we connect this to the grams and liters we actually measure in a lab or factory? That seems like a big leap.
It is, but it's where the concepts become really practical. The first step is figuring out the weight of these formulas. We use formula weights, FW, and molecular weights, MW. Think of the atomic weights from the periodic table, like the price per atom. The formula weight is just the total cost for all the atoms in the formula.
So for sulfuric acid, HSOO, you add up 2 hydrogens, 1 sulfur, 4 oxygens, using their atomic weights.
Exactly. Comes out to about 98.1 atomic mass units, AMU. And since HSO is a molecule, we can also call that its molecular weight.
What about things that aren't molecules, like salt, NaCl?
For ionic compounds like NaCl or, say, K-Laero, we use the simplest formula unit and calculate its formula weight the same way. It's the baseline weight for that compound's repeating unit.
And knowing that weight lets you figure out the elemental composition, right? Like what percentage of sulfuric acid's weight is actually sulfur?
Precisely. Imagine you're a forensic chemist with some unknown white powder. Finding out the percentage of each element is a key step in identifying it.
How do you calculate that?
You take the total weight of the element you're interested in within the formula. So for sulfur in HS-Aero, that's just the atomic weight of sulfur divided by the total formula weight of HAD and multiplied by 100.
So for HS-Aero, sulfur's weight, about 32.1 AMU, divided by the total weight, 98.1 AMU, times 100.
Yep. Gives you about 32.7% sulfur by mass. Every pure compound has a unique elemental composition, so it's like a fingerprint.
Okay, but we're still talking atomic mass units. How do we get to grams? How do we count these impossibly tiny atoms in real-world amounts?
This is the absolute cornerstone concept.
Yeah.
Avogadro's number and the mole. Trying to count individual atoms is just impossible. You mentioned a teaspoon of water earlier. It has something like 2 times 10 to the 23rd water molecules, an astronomical number.
Way too many to count.
So chemists needed a practical counting unit, like how bakers use a dozen for 12 eggs. Chemists use the mole, symbol mole.
Okay, so what is a mole? How many things are in it?
A mole is defined as the amount of stuff that contains Avogadro's number of particles, and that number is 6.02 times 10 to the 23rd.
Whoa, that's huge.
It's mind-bogglingly huge. There are analogies like if you had a mole of marbles, they'd cover the entire Earth miles deep. It's just a way to package an enormous number of tiny things into one convenient unit.
So a mole of carbon atoms is 6.02 by 10 more carbon atoms, and a mole of water molecules is 6.02 by 10 water molecules.
Exactly. A mole of anything is Avogadro's number of those things.
Yeah.
Atoms, molecules, ions, electrons, whatever you're counting. It's the bridge between the microscopic and the macroscopic.
Right, but like you said, a dozen eggs doesn't weigh the same as a dozen bowling balls. So a mole of different things must have different masses.
Absolutely. A mole is a number. The mass depends on what you have a mole of, and this leads us to molar mass.
Okay.
And here's the beautiful, simple connection. The atomic weight of an element in AMU is numerically equal to the mass of 1 mole of that element in grams.
Wait, really? So carbon's atomic weight is about 12.0 a mu.
So 1 mole of carbon atoms weighs 12.0 grams.
Chlorine is 35.5 a mu.
1 mole of chlorine atoms is 35.5 grams. It's the same number, just different units or mu for 1 atom. Grams for 1 mole of atoms.
Wow, okay, and that works for compounds too.
Yes. The formula weight or molecular weight in AMU is numerically equal to the molar mass in grams per mole, gmol. Water is 18.0 mu per molecule, so 1 mole of water weighs 18.0 grams.
That's incredibly useful. It directly links the periodic table numbers to measurable lab quantities.
It is. But you do need to be specific about the chemical form. For example, nitrogen exists naturally as N euro molecules. So 1 mole of N atoms is 14.0 grams, but 1 mole of N molecules is 28.0 grams. Context matters.
So molar mass is like the conversion factor between moles and grams.
Exactly. Molar mass lets you convert between grams and moles, and Avogadro's number lets you convert between moles and the actual number of atoms or molecules.
So you can figure out how many atoms are in something you can actually weigh.
Yep. Take an old copper penny, mostly copper, weighs about 3 grams. You can use copper's molar mass to find moles, then Avogadro's number to find the number of copper atoms.
And it would be a huge number, I bet.
Oh yeah, about 3 times 10 to the 22nd copper atoms in that single penny. It just reinforces how many particles are in even small amounts of stuff.
And this isn't just theoretical. You mentioned glucose monitoring.
Right. Diabetics measure glucose concentration in their blood, often in units related to moles, like millimoles per liter. Understanding these conversions between mass and moles is literally vital for managing their health.
Okay, so now we can weigh things, count moles, figure out percentages. This must let us figure out the actual chemical formulas of unknown substances, right?
Right, exactly. We can determine both the empirical formula and the molecular formula. It's like chemical detective work.
What's the difference again? Empirical versus molecular.
The empirical formula is the simplest whole number ratio of atoms in the compound. Water is H euro, and that's also its empirical formula because you can't simplify that 2.1 ratio.
Okay.
We can calculate this if we know the mass percentages of the elements. Say you analyze a compound and find it's 74.0% mercury, Hg, and 26.0% chlorine, Cl, by mass.
How do you get the formula from that?
Assume you have 100 grams of the substance. That means you have 74.0 grams of Hg and 26.0 grams of Cl. Convert those masses to moles using their molar masses.
Right, grams to moles.
Then you find the ratio of moles of Cl to moles of Hg. In this case, it comes out very close to 2.1. So the empirical formula is HgCl.
What if the ratio isn't a perfect whole number, like 1.98?
Good point. Experimental data always has some error. You round to the nearest whole number if it's very close, like 1.98 rounds to 2.
And how do you get those initial percentages, especially for things with carbon and hydrogen?
A common technique is combustion analysis. You burn a precisely weighed sample in excess oxygen. All the carbon becomes CO, all the hydrogen becomes HO.
And you trap and weigh the CO and HO.
Exactly. From the mass of CO, you calculate the mass and moles of carbon in the original sample. From the mass of HO, you get the mass and moles of hydrogen.
What if there was oxygen in the original sample, too?
You find the oxygen by subtraction. Total sample mass minus the mass of carbon, and hydrogen gives you the mass of oxygen. Then you convert that to moles. find the simplest mole ratio, and boom, empirical formula.
Okay, so that gives the simplest ratio, but sometimes the actual molecule is a multiple of that, right? The molecular formula.
Correct. Like benzene, its molecular formula is Ca euro, but the simplest ratio is 1.1, so its empirical formula is just CH. Acetylene is CH euro, also empirical formula CH. Different compounds, same empirical formula.
So how do you find the true molecular formula?
You need one more piece of information. The compound's molecular weight, which you might get from another experiment like mass spectrometry.
And then
You calculate the weight of the empirical formula, like CH is about 13 AMU. You divide the known molecular weight by this empirical formula weight.
that should give you a whole number or close to it.
It should give you a whole number multiplier. For benzene, the molecular weight is about 78 AMU. 78 divided by 13 is 6. So you multiply the empirical formula, CH, by 6 to get the molecular formula, CH.
Ah, clever. So vitamin C, ascorbic acid. Empirical formula CHEOEO, molecular weight about 176 AMU.
Okay, calculate the empirical formula weight for CHOs. It's about 88 though. Divide 176 by 88.
That's 2.
So multiply the subscripts in CHOs by 2.
CHO, that's the molecular formula for vitamin C.
You got it.
All right, bringing this all together. Why is doing these precise calculations based on balance equations so important in the real world?
Oh, it's critical for so many reasons. In industry, you want to use reactants efficiently. Calculating the exact amounts needed avoids wasting expensive materials. It also helps control the reaction. Too much of one reactant might lead to unwanted side products or even dangerous conditions like runaway reactions or explosions if gases build up.
And it probably makes cleanup easier, too, if you don't have lots of leftover starting materials mixed with your product.
Exactly right. Better purity, simpler separation, lower cost, safer processes. It's all about control through calculation.
And the key link is back to those coefficients in the balanced equation, right? They don't just balance atoms, they tell you the mole ratios.
Precisely. For 2 H euros plus O euros, the coefficients mean 2 moles of H react with 1 mole of O euro to produce 2 moles of HO.
These are the stoichiometrically equivalent quantities.
Yes. And that mole ratio from the balanced equation is the conversion factor that lets you calculate. If I start with X grams of reactant A, how many grams of product B can I make?
It's usually a 3-step process then.
Typically, yeah. 1, convert grams of your starting substance, A, to moles of A using its molar mass.
Okay.
2, convert moles of A to moles of your desired substance, B, using the mole ratio from the balanced equation's coefficients.
The crucial step.
3, convert moles of B back into grams of B using its molar mass.
Grams A moles B, A grams B.
That's the pathway. It lets you predict quantities across the reaction.
But what happens if you don't mix the reactants in that perfect stoichiometric ratio? Like you just dump 2 chemicals together.
That happens all the time. And it leads to the concept of limiting reactants.
The sandwich analogy works well here, I think.
It does. If a sandwich needs 2 slices of bread and 1 slice of cheese, and you have 10 slices of bread, but only 3 slices of cheese.
You can only make 3 sandwiches. The cheese runs out first.
The cheese is the limiting reactant. It limits how many sandwiches you can make. The bread is the excess reactant you'll have leftover bread.
So in a chemical reaction, one reactant gets completely used up first, and that stops the reaction.
Exactly. That's the limiting reactant. Any other reactants are present in excess.
Like when your car runs out of gas.
Perfect analogy.
Yeah.
Gasoline is the limiting reactant. There's still plenty of oxygen, the other reactant, in the air, but the reaction stops when the fuel is gone.
So all your calculations about how much product you can make have to be based on that limiting reactant.
Absolutely. The limiting reactant dictates the maximum possible amount of product. You have to figure out which reactant runs out first, and then base your calculation on that amount.
Okay, so the amount you calculate you can make based on the limiting reactant, that's the theoretical yield.
Correct. Theoretical yield is the maximum amount of product predicted by stoichiometry, assuming the reaction goes perfectly and you recover everything.
But reality is often messy. The amount you actually get in the lab is the actual yield.
Right, and the actual yield is almost always less than the theoretical yield.
Why is that?
Several reasons. Maybe the reaction doesn't go to completion. Maybe some reactants participate in unwanted side reactions. Or maybe you just physically lose some product during purification or transfer spills, stuff sticking to glassware.
Can the actual yield ever be more than theoretical?
No, that would violate the law of conservation of mass. If you get more than 100%, it usually means your product isn't pure. Maybe it's still wet with solvent or contaminated.
So how do chemists measure how successful a reaction was then?
They calculate the percent yield. It's simply Actual yield, theoretical yield, 100%.
So if theory predicts 50 grams, but you only isolate 40 grams.
Your percent yield is 40/50, 100 equals 80%. It's a measure of the reaction's efficiency in practice. Chemists and chemical engineers constantly work to maximize percent yield.
Wow. Okay. We've covered a lot of ground today, haven't we? From the basic idea that atoms are just rearranged conservation of mass, all the way through balancing equations, seeing reaction patterns,
Then figuring out how to count atoms using moles and molar mass determining formulas.
and finally using all that to calculate real-world reaction quantities, deal with limiting reactants, and understand yields. It really builds into a powerful framework.
It really does. And it's so important to remember, this isn't just, textbook theory. These quantitative tools are fundamental to, well, almost everything. Industrial manufacturing relies on it. Developing new medicines, creating new materials, finding environmental solutions like for climate change.
Even understanding our own body's metabolism, right?
Absolutely. And life-saving tech, like airbags. It all comes back to precisely understanding and controlling chemical quantities. This knowledge really does let you see the world on a deeper, more fundamental level.
So maybe something for you, the listener, to think about. Next time you see chemistry in action, maybe cooking, maybe a car engine, maybe just rust forming, think about the stoichiometry behind it and consider this. How could a deeper understanding of these precise ratios, these element measures, lead to even better, more efficient, more sustainable technologies in the future? What impacts might that have on our daily lives that we haven't even thought of yet? On behalf of the Deep Dive team, thanks for joining us today for this exploration into the quantitative world of chemistry.